Now we're at the second to the last page, and things are 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 things. Okay, and that was my previous attempt at recording. So I had a 30-minute video, and that started about 3 minutes from the beginning. So let's try this again. I think it was a pretty good video for my abilities. But anyway, here we go. Hi everyone, and welcome to this talk on deep learning. Before I get started talking about deep learning, I want to take a look at the ultra big picture, the picture of life, the universe, and everything. And life began on this planet about 4 billion years ago. And if we had a book series of life on Earth, and if each page of a book represented about 200 years, we'd need a library about this size, right? We'd need just stacks of books to represent that 4 billion years of life, and stacks of books. Now, humans came on the planet about 300,000 years ago, so that's about 3 volumes in that humongous library of books. And each page, again, represents about 200 years. And if we move from one page to another as we're reading along, not much has really probably changed. So the difference between 250, 200 BC and 250, 000 BC is not great, right? It's kind of a hunter-gatherer society, wooden spears, cooking. Next page, same stuff. So not a tremendous difference, sort of a boring read, that library of life on Earth. Or at least it's slow moving, pretty exciting in the grand scheme of things, but page to page is kind of slow. About 100,000 years ago, Homo sapiens developed behavioral modernity, which is when you got this ability to plan, to kind of reason, to do abstract thinking, art, music, all those things started about then. That's the last volume of the book. And we're still hunter-gatherers. And again, if we move from page to page, the page representing 9200 BC and 90000 BC, not much of a difference. Wooden spears, cooking, tools are made from bones, antlers, and clothes. So at least in the beginning of that last volume, page after page is pretty similar in life on Earth. 10,000 years ago, agriculture started. So that's about 50 pages to the end of the last book in the library of life on Earth, the last 50 pages. Agriculture has brought about phenomenal change in society. And again, though, if we looked at one page representing 5200 BC to 5000 BC, not much has changed. There's small communities, human settlements, domestication of animals, metal tools. That picture is really cool. It's the harvester's sickle, as you can read, and it's from 3000 BC, so showing that agriculture has been around for quite a long time. And then we're getting close to the end of that last book. Second to the last page, the United States of America, all sorts of innovation is happening in there. It's in the 1700s, and things are happening quickly. So the bottom to the second to the last page, trains came into existence, revolutionizing society beyond belief, and more automation of factories began. And that last page of the book is representing 1820 to 2020, and now phenomenal growth is happening. Now this last page, finally, when we started the first book, it was kind of boring reading. Now this is sped up incredibly, right? So in 1903, the Wright brothers, air conditioning, Ford Motor Company, all 3 things happened in 1903. Pretty amazing. The last paragraph of the book, personal computers, laptop, cell phone, iPhone. The iPhone's probably the last sentence in the book. So you can see there's this tremendous growth. So if we look at the previous page, the discovery or the independence of the United States, to this page, its difference is night and day. So it's an astronomical difference at 200 years. Even if we look at the last 50 years, so the last paragraph compared to the paragraph above it, phenomenal growth. There was no personal computer, laptop, cell phone, iPhone. Pretty much life as we know it is drastically different from 1970 to now. So it's this astronomical difference of what's happening. So if we were to kind of graph this out, this is from a great site called Wait But Why. But we have human progress versus time. And you can see that there's this little exponential growth here. And we're there, that little stick man, kind of on the edge of it. And if we were to look there and try to project out, we'd probably think the slope would be pretty similar. So the next 50 years should be pretty similar to what the last 50 years of progress has been. But that's wrong. That's not how things, as I've been hoping to demonstrate, work, right? We're just exponentially growing. That last page of the book was a lot more exciting than that, book 500 in the series. So this is where we're heading. We're on the cusp of some phenomenal growth in human development and technology. And what's driving that growth is artificial intelligence and deep learning. So that's where we are. And let me take a step back and talk a little bit about the road to superintelligence. Now, artificial intelligence, there's people typically divided into three categories. There is artificial narrow intelligence, or ANI, which is called weak AI, and that's where AI that specializes in one area. So a machine is good at one thing, really, really good at one thing. Artificial general intelligence, or AGI, is strong AI, and that means that one machine can perform any task a human can perform. So whatever you can do, one single machine can do. Artificial superintelligence, ASI, one machine performs everything better than the best human. So one machine is the best hip replacement surgeon, cancer diagnosis machine, chess machine, automobile, whatever. Whatever you can think of, this one single machine is the best at it compared to any human. So where we are now is a world run by artificial narrow intelligence, or ANI. Our whole life, every pretty much moment of our life, is impacted by artificial narrow intelligence. So any interactions with our phone typically involve AI. So there's map software, Pandora recommendations, weather, Siri speech recognition, song recognition on the phone. So we interact with our phone a lot. Cars are full of ANI systems. We have anti-lock brakes, tuning for fuel injection, self-driving cars, adaptive cruise control, automatic lane change detection, blind spot detection, tons of things in cars. Email spam filtering sounds boring, but it's really a fairly useful thing. Amazon recommendations. So, all those things we see Amazon suggesting to us. Google Translate and Pixel 2 music recommendation, and the list goes on. So from landing an airplane to determining what the ticket prices for that plane will be is determined by artificial narrow intelligence. Finance, 1/2 the stocks in the stock market are traded by ANI. It led to this thing called a flash crash. $1 trillion were lost in that one crash. Medical diagnosis, phenomenally successful there. The military, obviously, Facebook. And we're using ANI all the time. So our life is impacted by ANI for the better. Our society is changing dramatically. And just an example of that is this research done way back in 2016 is Hemingway's The Snows of Kilimanjaro. So obviously it was originally written in English, and it was translated into Japanese by professional translators. So we have a good version of Japanese. And now this professor at the University of Tokyo decided, well, what happens if we have Google translate it back into English? So originally in English, professionally translated to Japanese, and now we're translating it back to English using Google Translate. What will the results be? So prior to November 16, this is the result. So one of these is the Google Translate system, and the other is the original by Hemingway, and I'll have you look at it and determine which is which. And if you think it's the first one, you'd be correct, right? You can get kind of a rough idea of what it's about, but it's not great English. Kilimanjaro is 19,710 feet of the mountain covered with snow, and it is said that the highest mountain in Africa. Top of the west, Najiji Nagai in the Maasai language has been referred to as the house of God. The top close to the west, there is a dry frozen carcass of a leopard. Well, you get the idea here. You get the idea here. It's not so bad, but it's not, you wouldn't be reading a novel written by Google Translate. But in 2016, Google changed their algorithm to a very deep learning system, and the quality dramatically changed. So here's the result of that one. It's the top paragraph here. Kilimanjaro is a snow-covered mountain, 19,710 feet high, and it is said to be the highest mountain in Africa. Its western summit is called Maasai Najiji Nagai, the house of God. Close to the western summit, there is the dried and frozen carcass of a leopard. No one has explained what the leopard was seeking at that altitude. So you see that it's phenomenally better than that previous version all due to that deep learning and all due to this phenomenal exponential growth in the quality of artificial narrow intelligence. So we're at this junction. So we have this artificial narrow intelligence, ANI, weak AI, and we're moving toward artificial general intelligence or strong AI. And there's two keys to this. One is computational power, and the other is just lots of data, and more data. So here's one graph. Raymond Kurzweil did this back a number of decades ago, but comparing what the calculations of a $1,000 computer can do compared to compared to life. So back when he wrote it, $1,000 computer was equal to one insect brain. And so he was projecting out here and kind of was assuming right around now we'd be equivalent. $1,000 computer would be as powerful as a human brain. And we're not far off. Let's see how this works. So here, this is an amazing graphic that I'm kind of interested in showing you. And this is how long until computers have the same power as the human brain. And I'll just read the text here. Lake Michigan's volume in fluid ounces is about the same as our brain's capacity in calculations per second. Computing power doubles every 18 months. At that rate, you see very little progress for a long time, and suddenly you're finished. Usually, when you read this, you think, yeah, I can kind of understand it, but just seeing visually kind of makes it sink in about how fast that last bit of growth is. And there it is. It's just totally amazing. So back in 1940, whenever it started, computers were at 1 instruction per second. And it doesn't look like we're doing much, but then all of a sudden it grows off. And you see it's around now that the phenomenal growth occurs. So that's really a pretty cool graphic, I think. All right. So according to Kurzweil, a human brain is about equal to 10 teraflops, floating point operations a second. And right now, this is my older computer. You can see all the dust on it, but it does 8.2 teraflops. So it's getting pretty close to a human brain, at least according to Kurzweil. And you can see the technology isn't that new. It has an older graphics card, and all that power, the teraflops, is in that graphics card. But there's new stuff out on the market. So the head of NVIDIA here is demonstrating the Quadro GV, or holding up the Quadro GV100, which is 15 teraflops. And you can put those together and get a 2 petaflop computer for around $400,000. And the phenomenal thing here is that the previous model that was made 5 years ago compared to this one's 500 times faster. So when you look at the speed of growth of computational power, it's phenomenal. So things are not stagnated whatsoever, that we're having this phenomenal growth in computational power. So in deep learning, we need that phenomenal computing power that I just talked about, ginormous data sets, which we're getting just because of the aspect of everything's on the web and connected, and cool algorithms. Let's not discount the human mind and the creativity involved in figuring out how to create deep learning systems. And deep learning has transformed everything from speech recognition. That's the best improvement in 20 years for sure. I've worked in speech recognition a long time ago, and the quality today is phenomenal. Breast cancer detection and ultrasound imaging, human experts are about 87% accurate. Deep learning systems are 99.999% accurate. And finally, Google Translate. I just showed you that example. It's just really phenomenal of the growth in the improvement made in deep learning. And I should also point out that when you think about artificial intelligence, you're really thinking about deep learning. It's hardly anything uses artificial intelligence that is not deep learning. They're not synonymous terms, but the main progress in artificial intelligence is in this system of deep learning. So again, deep learning, the big bang of machine learning, because of 3 main impacts. There's 3 influencers of the big bang. One is the just vast improvement of the solvers in deep neural networks and different techniques such as convolutional neural networks. Probably started around, 2012 with the advent of AlexNet, a big network that solved image classification problems. The next one is the big data movement and just the vast volume of data. It's like 2.6 quintillion bytes of data are generated every day. So it's just a humongous amount of data being provided to us. And that third element of the Big Bang is just the sheer increase in processing power. So that's the Big Bang in machine learning. And this brought about a tremendous difference in workflow of how people in machine learning work in the field. So before neural networks, a lot of the time was spent in classical machine learning, you doing hand-designed features, manipulating the data in certain ways, just to prepare the data for the machine learning algorithm, whether it was a regression algorithm or support vector machine. So that's kind of traditional machine learning where most of your time is spent in data preparation. In deep learning, not so much. There's some preparation involved, but a lot of it is handled by the deep neural network itself. So that's the difference in workflow between hand-designed features and ones that were just kind of giving that the raw data, not exactly the raw data, to a deep learning system. So the example here was with the digit. So the idea began in 1943, the idea of kind of neural networks, not deep neural networks, by this paper, A Logical Calculus of the Ideas Immanent in Nervous Activity, in the Bulletin of Mathematical Biology by McCullough and Pitts. That kind of started the idea of what's called artificial neural networks, or perceptrons as they were called in those days. The original idea was that it was sort of like neurons in people, but now we don't care whether it is or not. We're not biologists. We don't know how neurons work. At least I don't. The idea is a good one, and we can call it neurons. But just keep in mind that, who knows how this is related to how people do things. It's just an analogy that we're using. So don't put too much stock in the term neuron. And the idea from that original paper, or very simply, is this, that we have a neuron, that's the one with the summation sign there, and it has a number of inputs like x1, x2, however many inputs it has, in addition to one constant input, x0, which is always 1. And each of those inputs in the neuron, it also has an associated weight. That's the weight 0, weight 1, weight 2, weight n. And we simply multiply the input, x1, by the weight, w1, as an example. We do that for all the neurons, and then we sum them up, and then we have some sort of activation function. When is that neuron going to fire, in some analogy, right? So our little output formula is that it's going to output 1 if the summation is larger than 0 and -1 otherwise. So as you can see, it's kind of a very simple idea, right? We have these neurons. They take input. So there's a value, x1. Within the neuron, there's an associated set of weights, and we just multiply these together, sum them up, and see what the result is, determining what the output should be. That's it presented kind of in a mathematical way. And suppose we're trying to do a truth table like logical AND. So if input x1 is 1 and input x2 is 1, and we're trying to do this logical AND, we want to output 1. And in other cases, we want to output 0. Well, in my little example, we want to output -1, but let's go with it. So there's the perceptron, and my question is, can you figure out what those weights should be? What W0, W1, and W2 should be? And there are many answers here. It's not a single answer. There's many good ones. Here's one of them. So W0 can be -1, W1, 1, and W2, 1. So when we have an input like when x1 and x2 are 1, so that's when we do want to output that 1. There's our little calculation that x0 is always 1. We multiply times the weight, -1, and get -1. Do the same calculations for x1 and x2. And when we add those up, -1, 1, and 1, we get 1, and that's larger than 0, so we're going to output 1. So that makes good sense. And here, when x1 is 1 and x2 is 0, logically we want to output -1 in this case. And you see we do, right? So we have -1, 1, and 0, so that all adds up to 0. And our output function is we output that -1. So obviously, the simple perceptron can do the AND. What about OR? So there's the OR. So if one of those, if x1 or x2 input is 1, we're going to output 1. And there's that perceptron again. And again, the question is, can you figure out what it should be? And here's one solution, that if W0 is 0, that weight is 0, and 1 and W1 and W2 are 1, then this will work, right? So here's a case where just x1 is 1, and we want to output 1 with the OR condition, and we do. So you get x0 being 0, or x0 times w0 is 0. The x1 line, the output is 1 and 0. We add those up and get 1, so we output 1. And when neither x1 and x2 are on, or they're both 0, we're going to output -1. So what about XOR? Can you figure out XOR? So XOR is when if x1 or x2 are 1, then we output a 1. But if both are active, both have 1, we should output a 0. And if you stop the video and worked on this for a bit, you'll not come up with anything, that's exactly the correct answer, because you can't have an XOR with this simple network. And this simple realization, which occurred kind of early on in the history of perceptrons, stopped funding of artificial neural networks. So it came to the belief, well, if I can't solve XOR, what can it solve? But people didn't realize the complexity. It was kind of an artificial criticism, because we can make networks much more complex than this simple one that can handle XOR and do machine translation and do all sorts of things. So it was kind of a fake, not a fake, it was an accurate description, but it kind of stopped research. It created this winter in neural network research. So here's the idea in artificial neural networks. So let's say we have some sort of inputs. That's the data set there, those boxes, and we want some output, the circle. So let's say we were trying to do a self-driving car, and all those inputs are different sensors in the car. So that orangey box is, I don't know, the distance between you and the car in front of you, and we get some other indications. We have some LiDAR and information like that. And that circle represents the turning angle we want to turn in. So we feed that, that's on the bottom there where we have x1, x2, all those inputs, those boxes, to our neural network. Those are all the circles in the middle. And we do that summation that I just showed you. We multiply the sensor value by some particular weight, and we sum all those sensor values, feed them to all those intermediate circles, and it's going to make some output or prediction of the steering angle of the car. And we know the target angle, that's the dark blue there, that came from our data set, and we compare the two. That's on the bottom where we say error equals whatever it is. We figure out, well, this is what our system output, and this is what we intended it to output, and we get some number representing the loss, the error that it produced. And in this case, it's 5. Knowing that we produced this error, we can kind of adjust the weights on these different arcs. So let's say we adjust this one, and we run the algorithm again through the data, and we get some sort of comparison between, now our output is that light gray. Let's say that means turn left 15 degrees. Who knows what it really means. And our output was turn right 90. So a huge difference. And we compute that error, and we get 15. So that's the error rate. And we'd make another adjustment. So we keep doing these adjustments, right? So we can see the results of our weights. If the weights weren't good and produced bad results, we're going to adjust those weights to get a closer approximation of the correct answer. So that's the idea of deep learning. So in forward propagation, we take input, like maybe a picture, and we multiply each pixel by some weight, and that's going to represent the value within the neuron. We do that summation, and we keep propagating this throughout many, many layers of neurons, and our output's going to be, what neurons lit up. It lights up for a cat, or it lights up for a dog. So that's kind of the idea of forward propagation. Now we compare the results. How did this compare to what we wanted? And then we do a backward propagation. So we compute some sort of loss, the difference between what the label should be. This should be a dog, and we said it was a teddy bear. And we back propagate that error so we can adjust the weights of the network. And then we do it again. We do that forward propagation, see what the results are. See if there was a little error. We adjust the weights going backwards. So we keep repeating this process over and over and over again. Multiple iterations over the data to adjust these weights. One thing to note is that there's an activation function. So after we do this summation, what should be the output of that neuron? So in this case, we use the unit step. It looks sort of like a step. And that output function is, just kind of a binary. If it's this, we do this, and -1. Otherwise, it's really a stepwise function. And there can be other ones. There can be a ReLU, which is the rectified linear unit, which if it's less than 0, we output 0, and otherwise we do kind of that angled output. So the output's more linear. We can do a softmax, which is more probability, used for classification. We'll talk about these at length later on. I just wanted to kind of introduce this idea that we just aren't doing if this, kind of a simple if else statement, but more complex output functions. So here's an example from a few years back where I was trying to recognize car pictures, whether it's a picture of the side of the car, the front of a car, back of a car, kind of angle picture, the picture just of a tire, interior picture. And here we see the results. So it's kind of the probability. So we see the scores represented, and we're going to pick the label that has the highest score. In this case, I'm 75% confident that it's a picture of the side of a car. Cool. So that's how it works. So we have this untrained neural network that just randomly selects weights. And then in training, we're adjusting these weights to do better and better on the training data. And what I've shown you so far is a very simple architecture. We have one hidden layer. A hidden layer is one that's in the middle between the input and the output. So that layer in between is called a hidden layer, and it's fully connected. And what I mean by that, I'll show you in a second. So here's our standard example of recognizing a digit in a 28 by 28 image, right? So it's 28 by 28 grayscale, and there's just another version of that. And there's the example of the array. So that picture that we see is represented by a 28 by 28 array going between 0 and 1. That's the values. And then we're going to flatten that image, at least for this very simple neural network. Later on, when we work with convolutional networks, we're not going to do that. But in this case, we're flattening it just to have a long string of 784. And then each of those pixels is going to be connected to each of the neurons. This is a very simplified picture that only shows some of it, but you can see that each pixel is connected to that fourth neuron in the middle. And it's true with each of those pixels is connected to the first one, the second one, the third one. It just would look complex to draw. And then in turn, each of those middle neurons are connected to each of the output neurons. Again, I'm just showing one connection here. And in a second, I'll show you a little bit more. There it is. And now you can see where it's hard to understand what that picture is. But every pixel is connected to every neuron in that middle hidden layer. So that's what it means by fully connected. Fully connected network, everything's connected to everything pretty much. So that's all I wanted to cover. So lab 1 kind of explains things in a bit more. It's a bit hands-on. It's a little different, this talk, than the previous ones where I stepped through stuff in a Jupyter notebook. But I think it's better just to have this hands-on experience, and then we can regroup and have a little chat about what we learned. So that's it for now. Thanks so much for listening and watching this video. Take care. Bye.